hearty welcome to today's chemistry session. In this session, let's discuss about valence bond theory. You know, valence bond theory is very important in the point of view of exam. So here, we'll take some frequently asked questions, and based on that, I'll teach you how to use VBT to explain the hybridization and its geometry and its magnetic behavior for a given coordination compound. Let's see one question. Here, one question is given in different formats. You can see here, using VBT, explain the geometry of NiCN4 2-. That same question is asked in another way. Write the hybridization and the shape of NiCN4 2-. For NiCN4 2-, describe the stereochemistry and magnetic behavior. You can see here how frequently this same question is asked in different ways in Cbse board exams. So, let's discuss about in detail. This is the given complex NiCN4 2-, that is the given coordination compound. So the first thing, this is the easy method I am explaining to you. First thing what you have to think is, what is its atomic number? The central metal ion, what is the atomic number? That is 28. Then we have to write its electronic configuration. So Na will have the electronic configuration argon 3d8 4s2. That is its electronic configuration. That is the first step. Next step is to find out the oxidation state of the central metal ion. That you know, you have learned already. So here each Cn is having 1- charge. So here it is 4- charge. So this will be 2+. So the coordination entity is carrying a 2- charge. Okay. So this Na is in +2 oxidation state. So we have to write the electronic configuration of Ni2+ ion also. Ni2+ is having the electronic configuration. 2 electron is lost from it. So it will have the electronic configuration argon 3d8. This is the electronic configuration of Ni2+ ion. And now we can only concentrate on this outer orbital. We cannot draw all the orbitals here. So we will concentrate only on the outer orbital. So Ni2+ we can draw it like this. This is the outer orbitals will be like this. This is the 3d orbital. Okay. Now we have the 4s orbital. Then we have the 4p orbitals. These are the outer orbitals of this particular ion, Ni2+ ion. Okay. Now we have this 4s and 4p are empty here, and then 3d, in the 3d orbital we have 8 electrons. So following the Hund's rule of maximum multiplicity, we are allotting those electrons in this 10, in this 5 sets of orbitals. 1, 2, 3, 4, 5, 6, 7, 8. 8 electrons are there. Okay. So this is the actual electronic configuration of Ni2+. Now next step is very important. Central metal ion is in this state, and now a complex is going to get formed. Coordination compound of NaCN4 2- is getting to form. Now you can see here, next step is the formation of the coordination compound. NiCN4 2- is formed. We are showing its formation, how it is getting formed. So we have to see this ligand that is attached to the central metal ion, whether it is a strong field ligand or it is a weak field ligand. That is very important. See here you have, these are the strong field ligands. CO, Cn-, En, NH3, NO2-. So you have to see whether this particular ligand that is attached with the central metal ion is any one among this. Yes, we have Cn-. This is a strong ligand. So when a strong ligand approaches the central metal ion, its field strength is very strong. So what they will do? They will push these electrons that are arranged according to the Hund's rule in the orbital to get it paired up. So the electrons are compelled to disobey Hund's rule and to get paired and arrange themselves as closely as possible. Okay, so what happens? We'll see here. When Cn minus ligands approaches, these electrons which were arranged themselves in the orbitals according to Hund's rule of maximum multiplicity is compelled to get paired up. So what happens here? 1, 2, 3. These two electrons which were in two orbitals were compelled to get paired. So 2, 4, 6, 8. Those 6 electrons are again rearranged into another set of 1, 2, 3, 4. 4 pairs, as they are existing as pairs right now. The same thing, 3D here. Anyway, it is against the Hund's rule of maximum multiplicity. Now we have 4 s orbital here, 4 p orbital also here. So the strong ligands, you see how many ligands are here? 4 ligands are here. Each ligand will give a pair of electrons. That is a coordination, that is the formation of coordinate covalent bond. Each ligand will give a pair of electrons and they will take place of this central metal ions orbitals and they will form equal number of hybridized orbitals. If 4 ligands come and take the place of this central metal orbitals of central metal ion, equal number of hybrid orbitals will be formed, new hybrid orbitals. You can see here. So this is one pair of electrons of Cn minus ligand. So this is the second pair. We have 4 pairs of electrons from the Cn minus ligand. Third pair, fourth pair. So ligands have already taken place and the formation of NiCN42 minus happened. Now you can see. This is 3D, this is 4s, this is 4p. Okay. Now you can see here. Among this 3D, one is involved in the formation of a hybrid orbital. So D, 1s is also involved, ds, 2p are involved from the orbital. So dsp2. So this is the hybridization of this particular coordination covalent bond, coordination complex, dsp2 hybridization. So you know that if it is a dsp2 hybridization, the formed complex will have the geometry of square planar. So it will have the square planar geometry. So once you know the hybridization, you can predict the geometry. We have already explained in the last session. So it will have square planar geometry. It will be existing in square planar geometry. So we have predicted its hybridization, we have predicted its geometry, and then coming to the magnetic behavior, whether it is paramagnetic or diamagnetic. This is diamagnetic. Why it is diamagnetic? This particular complex is diamagnetic in nature. Why it is diamagnetic? Because absence of unpaired electrons. If it should be paramagnetic, unpaired electron should be present. But we have all electrons paired up. So it is diamagnetic in nature. And then whether it is a low spin complex or whether it is an inner orbital complex or outer orbital complex. It is an inner orbital complex. You know that for inner orbital complex, it should be n-1, ns, n-1d, ns, np should be involved in hybridization. So here it is 4s, ns, 4p, np, then 4 minus 1, 3d, n minus 1d. Okay. So n minus 1d, n minus 1d, ns, np. Okay. 3d, 4s, 4p are involved in hybridization. So it is an inner orbital complex or low spin complex. Inner orbital complex or low spin complex or low spin complex. Okay. If it is 4s, 4p, 4d, it will be outer orbital complex or high spin complex. So you have explained everything about this particular coordination compound by using VBT. So you will get a full mark by writing all this. Writing all these steps, you will get full mark. It is very easy. I think we will explain few more examples later. Okay. So this is the end of our session today. I hope you have understood VBT very easily and very clear, I think. You can use it in the same way and you can find out, you can predict the geometry, hybridization, magnetic behavior, whether it is outer orbital complex or inner orbital complex very easily by using this method. So this is the end of our session today. Thank you. See you again.